Okay, welcome back everybody. Example 6.6 in chapter 6 of forces. This deals with Newton's third law. Very much like the canoe problem in example 6.5, but this one deals with something, well, it's just named differently really, called a contact force, right, or the force of contact. And I'll describe what that is a little bit later. It's nothing you don't have already. It's just kind of another way of naming something. But let's kind of look at the scenario right here. We have a tabletop. It's a smooth horizontal floor. So what that's assuming is zero friction. Okay. It's not really practical to think about that in the real life because everything has friction, but it's virtually frictionless. All right, so there's no friction holding it back. And we have two boxes with two different masses. Box 1, we'll call this mass 1, is 10 kilograms, and box 2 is 5 kilograms. And both of these boxes, this whole two-box system, is being applied, or a force of 20 newtons is being applied to it. It's really being applied to box 1 right here, but then we know from Newton's third law right here, Newton's third law, that for every action there's an equal and opposite reaction. Really, why is box 2 moving? You say, well, because box 1 is in the way and it's pushing it. But you could really say that box 1 is applying a force onto box 2. And because of Newton's third law, in the same way, box 2 is applying a force back onto box 1. So we should call this one right here force of 1 onto 2, all right, and we'll call this from 2 onto 1, just like that, so that it shows kind of like where the forces are coming from and where they're going. So this is from 1 to 2. So this is really the force acting on box 2 right here. So this whole system is going to be accelerating. That's what part A is asking us. What is the acceleration of the boxes, or you might say of the two boxes of the whole system? Well, we can do that. So we're going to set that up in the next on the next slide right here. All right, so I'm going to go ahead and draw my two-box system again. So here's in fact, here's a tabletop right there. All right, I got box 1, a big box, and a smaller box. Oops, I don't want to do that. A smaller box right up against it. I know they look like they're floating on the tabletop, but just pretend they're touching, okay? And it's supposed to be frictionless anyway. So this mass is of 1 equals 10 kilograms, and this mass right here, 2 equals 5 kilograms, and there's this 20 Newton force. We're just going to call it F, or you might say the force on 1 and 2, that's a 1 comma 2 right there, is 20 newtons, okay? So A is asking us, what is the acceleration of the boxes? What is the acceleration of 1 and 2? All right, well, here's where we can think of these two boxes as one system. Think of it like this, that you have one big mass right here that is kind of shaped oblong like that, and the mass of the whole thing, mass of the system, equals 15 kilograms. All right, well, that's exactly what's happening right here. The force doesn't care if they're connected or not. It just knows that it's moving one big mass, and so we can say, all right, so the mass of 1 and 2 equals 15 kilograms, and the force being applied to that mass, 1 comma 2, is 20 newtons, right? 20 newtons, because force are measured in newtons. Sorry, so what is that acceleration? We should be able to apply Newton's second law, right? And so Newton's second law, right now you're probably thinking, wait a minute, I thought this was a Newton's third law problem. Well, it is, and that's what the contact force is going to be. But for right now, let's just find the acceleration. All right, that tells us the net force on a system or an object equals the mass of that system or object times the acceleration. If we were to solve for acceleration, that would be the net force on that system or object divided by its mass. In this case, it's the force on 1 and 2, and the mass of 1 and 2. We call it the net force, but really it's the only force. There's only one force, this guy out here acting on this whole system right here. So what is that force? Well, that's 20 newtons, right? And the mass of the whole system is 15 kilograms. All right, so all we do is divide, and then we get our acceleration of that whole system. In fact, I'm going to put acceleration of 1 comma 2 because that applies to both boxes. Both boxes are accelerating at this rate. And that's going to be 1.33 meters per second squared. All right, our whole system, both boxes, are accelerating at 1.33 meters per second squared. So that's our answer to part A. Pretty easy. Really just an application of Newton's second law. Net force is mass times acceleration. But here in part B is where we get, we start to use Newton's third law. So the question is, what is the force of contact between the two boxes? All right, well, here's where we look at Newton's third law and say, what is that? Okay, well, that's for every force, there is a force of equal magnitude, but in the opposite direction that is also applied. So think of it as like this. Two people they're putting their hands together. All right, so this person right here, got kind of square thumbs. I don't know why that is. All right, two people pushing their hands together. This person is pushing with a force on that person's hand. Call that force 2, and this person is pushing with a force 1 on that person's hand right there. And let's say each person had a little force meter in between on the palms of their hands, or you might say a little teeny tiny scale. All right, is it possible that one person's force would be greater than the other person's force? And the answer is no. You can't push on somebody else without feeling the exact same pressure back on you. And so we can think of this as being the contact force. You might say the magnitude of both of these forces is the contact force between those two objects. That's exactly what's happening right here. All right, the force from 1 to 2, all right, force from 1 to 2, or 1 arrow 2, and force 2 acting back on 1 is the contact force between these two boxes. And it's really, look at box 2 right here. The only thing that is acting directly on box 2 is box 1. So that contact force is what's making box 2 move. So here's what we can do to solve for this contact force, since we don't know what it is, but that force in between the boxes. What is that? Let's look at each box individually. Okay? Now we can pick one or the other, because since we know these two forces are equal in magnitude, just opposite in direction, we can pick either box we want. I guarantee you, the way we calculate it out, both of the magnitudes of these forces will be exactly the same. But you might do well to pick whichever box you think is easier. So look at those two boxes right here. All right, which one has less going on it? You know, box 1 has the original force plus this force pushing back. Box 2 only has this one force right there. That's less going on, which means it might be easier to solve for. All right, so I'm going to write for box 2. Let's draw it out. All right, let's just kind of sketch it. What's going on with box 2 right here? We know the mass of 2 equals 5 kilograms. That's easy enough. All right, it's writing on the tabletop right here. And we know the force acting on it, well, that's what we're solving for, right? So we're going to call that force from 1 to 2. That's what we don't know. By the way, that is the contact force, right? The contact force is pushing box 2. But what else do we know about box 2? We know the acceleration, right? Because that whole system is accelerating at some rate right here, which means this box and this box are moving at exactly the same rate. So we can say, great, we know the acceleration of box 2. That is 1.33 meters per second squared. That's helpful to know because now all we need to do is apply Newton's second law. That is, the net force on box 2 equals the mass of box 2 times the acceleration of box 2. The net force, well, there is only one force, and that's the contact force, right? Force of contact. We also have been calling it force from box 1 on to box 2. Is going to be, what's the mass of 2? That's 5 kilograms times the acceleration. All the boxes in this system are accelerating at a rate of 1.33 meters per second squared. And so this will give us our force of contact. So 5 times 1.33, that gives us about 6.7 newtons of force. We'll call it force from 1 to 2, or you might say the force of contact, force of contact is going to be that 1.67 newtons right there. I'm not going to do it. You can try it if you want. But if we were to look at box 1 right here, this original force and plus this unknown force pushing back on box 1, creating the acceleration given the box 1's mass, we would find that it's exactly the same magnitude as it is pushing onto box 2, just in the opposite direction. All right, so you have to set up a little bit more. The net force on box 1 is a little more complicated because it's that plus that, but you get the exact same thing. So the key here is that this contact force is the force between these two objects, and it is really an application of Newton's third law, that for every force, there's an equal and opposite force applied to the other object. All right, so that's example 6.6. That's an application of Newton's third law, and I can tell you that one of your homework problems is very much like this. It deals with 3 boxes instead of 2, but you would set it up exactly the same way. So I hope that helps. Please come see me or contact me if you have any questions. And thanks for watching. I'll see you on the next one.